Hello everyone, my name is Alex and welcome back to part 2 of my AVL Tree series. If you haven't watched part 1, please make sure to watch that as it goes over the theory side of AVL trees. And in this video I will be showing my C++ AVL tree project that performs insertions, deletions, searching, and different traversals. I developed the project in Linux, so let's get into it. So let's start with a refresher on AVL tree. It's a self-balancing binary search tree that keeps height differences between left and right subtrees within one. So let's get into it. So first I have 5 different files. I have avl.cpp, avl.h, avltest.cpp, menu.cpp, and menu.h. So I did this for reusability and to have a neat setup for my project that can be extensible and easier to modify for the future. So let me go through each file and tell you what the purposes are. So for the avl.h, it declares the AVL class and its methods. For the avl.cpp, it implements all of the logics such as the rotations, the balancing, and the traversals. And the menu.h and menu.cpp files handle the user menu interface. And lastly, the AVL test.cpp is just the main driver that runs the menu and the project. So let's get into some of these files and explain some of the code. So let me get into the first file, avl.h. So in this file, I have an AVL. In this file, avl.h, I define my AVL class. It has a private inner class called node, which stores key value and keys, value, and the height, and pointers to its left and right children. And in the private section, I also have some helper functions like I have rotate left, rebalance, rotate right, insert, erase, and then I also have a private section here which has the constructor and the copy and the destructor, and then I have a function to insert, erase, and to find the key and to traverse. So let's quit out of that file and go into the next file, which is avl.cpp. So in this file, let me put this full screen. In this file, it contains all the actual implementations. So let's go to where I perform the rotation. So let's talk about this function right here, rotate right. So this function basically rebalances a left heavy subtree. And then we could go into the next one right here, rotate left, which handles the right heavy cases. So let's talk about the one right here for a second. So if a node becomes unbalanced with a balanced factor of greater than 1, the tree performs a right rotation so that its left child becomes the new root. And then similar, the rotate left does the same thing, it just handles the right heavy cases. And then I also have a rebalance function which checks the balance factor and decides which rotation will need to occur. And then I have the insert and the erase. So these are pretty self-explanatory themselves. They either insert or erase the binary search tree, but include calls to rebalance so that after every modification, the AVL tree automatically stays balanced. And then finally, I implemented see right here, the pre-order, which is root left right, the in order, which is left root right, and then the post order, which is left right root, and lastly the level order. Okay, so that's my avl.cpp. So now let's go into the menu.h. So in menu.h I have menu.h. So in this I have enum option, insert node, delete node, search node, traverse tree, display tree, level traverse, and exit. So basically why I did enum was for readability and reusability. So it just makes the code cleaner. As you could see, you could just see everything one by one. I have comments here of what each option will be. So this is just the header file. Let me get into the .cpp to show you guys a little more. So in this file, I include my menu.h, so just to make sure I have that header file included. This is just what the user will see, so it'll see out, please choose one of the following options, and it'll go 1, 2, 3, 4, 5, 6, 7. So the first one is insert key value, the second one is delete the key, the third is search the key, 4 is traverse, and 5 is display structure parentheses plus balance factors, and then 6 level order traverse, and 7 exit. So here the menus runs, and basically depending on what the user selects, it calls the right AVL function. For example, if the user selects the first, which is insert node, it will run that function. And yeah, so it will ask you to enter a key, and then it'll store that key, and then to enter a value, it'll store that value, and then it'll call that function and say that it was inserted. Same thing with all of the rest of these cases. And then of course right here, if the choice is invalid, it'll break out, and then 7 will be to exit the program. So let's get into the actual interface now. So let's do 1 second here. So let's run the program. So do g++ avl test.cpp avl.cpp menu.cpp dash avl. That should run the program. Let's give it a second here. It's taking a while to load. Let me do it again. CPP AVL CPP CPP. Here, I did it earlier. Let's see if I could get that same. Not sure why it's not working. Okay, so now I just gotta compile it. So I did /. So let's enter that. Okay, so now we are in our menu. So let's get into it. So the menu appears. So let's go with the first choice, insert a key value. So let's do let's insert 50 and then value 50. Well, let's enter a couple more here. Let's enter 30, value 30. Let's do it one more time. So we just have a couple of examples here. 70, value 70. Okay, so now that we did this, let's enter choice 4 to see if they actually print in order. So let's click in, and as you can see, they're in order right here. So that's working well. So now let's try to delete one. So let's go enter the key to delete. Let's do 30. So it gives us enter key to delete, deleted key 30 if it was present. Okay, so now let's check with if it was deleted. So let's go to choice 5. And yeah, so we're not seeing that value 30 anymore. We're just seeing these two right here. So it did work. So my program's running well. And as you can see, everything is looking good. So now let's see if it'll exit the program. Yep, exiting program. So yep, that's the end of my AVL tree video. So as you can see, the project handles the insertion, deletions, search, and multiple traversals, and makes sure that the trees stay balanced throughout the rotations. This makes sure that it keeps the time complexity for every operation at order log n, and that is what makes AVL trees so efficient for lookups and updates. So thank you guys for watching, and I hope you enjoyed the video, and stay tuned for the next one. Thank you.